Ever wondered where piles of old newspapers and boxes disappear? Every day, recycling centers process thousands of tons of paper waste, sorting it in seconds and transforming it into fresh sheets. Picture this: massive hangars, conveyor lines as long as a football field, sorting machines equipped with optical sensors, and drying cylinders heated to 260 degrees Fahrenheit. In just 5 to 7 cycles, paper fibers are reborn, becoming packaging, notebooks, or even furniture. Let's dive into the secrets of paper transformation. Think old newspapers or cardboard boxes are just trash? Think again. They have a future. It all starts simply. Paper and cardboard are collected. That includes old magazines, packing boxes, and even crumpled receipts. From there, the sorting begins, dividing materials by type and quality. For instance, cardboard is denser, while office paper is thin and clean. Sorting is a crucial step in giving paper a second life. So, let's break it down, step by step, in vivid detail. First, meet the key players in the process: machines and people. At large recycling centers, automated sorting lines handle the bulk of the work. But human hands are still essential. Operators on conveyor belts carefully check the paper's quality. It's a teamwork scenario where machines do the heavy lifting and people fine-tune the details. Recycling centers often look like giant hangars filled with mountains of raw material. Stacks of old newspapers, cardboard boxes, office documents, and even postcards. Here, conveyors roar and automated sorting systems buzz, processing everything. Here's how it works, step by step. First up, the initial inspection. Once collected, garbage trucks or special vehicles deliver the paper to the sorting center. At this stage, large contaminants like plastic wrappers, fabric scraps, or glossy-coated materials are removed by hand. Next, the automated machines take over, sorting paper by type and quality. Types include cardboard, newspapers, office paper, glossy paper, and packaging. Quality-wise, it's about separating clean paper from dirty, like sheets with grease stains or adhesive residue, which can't be recycled. Optical sensors and air filters play a big role here. Sensors scan the paper, while compressed air streams direct materials into their respective categories. Cardboard goes left, newspapers go right. Even the best machines make mistakes, right? That's where human operators step in to remove leftover foreign objects, like tape, staples, or plastic windows from envelopes. This process moves fast and demands sharp attention. After sorting, the paper is compacted into massive bales for easier transport to factories. Imagine blocks the size of a refrigerator, neatly packed and ready for a new life. Fun fact: old newspapers are easier to recycle than glossy magazines. Why? The glossy coating is harder to remove. Office paper, being high quality, often gets turned into new sheets for printing or even toilet paper. Next comes shredding and cleaning, the phase where old paper becomes the base for new material. Think of it as a paper bath, with powerful machines that not only shred, but also meticulously clean the paper of any impurities. Let's dive into the details. Compressed paper bales go into hydropulpers. Sounds intense, but these are just giant mixers. The paper is soaked in large amounts of warm water to help separate the fibers. Why water? It softens the paper, breaking it down into its cellulose fibers. Special chemicals, safe for the environment, are often added, like soap or alkaline solutions, to remove ink and glue. The hydropulpers kick into action, spinning water and paper at high speeds. The result? The paper breaks down into microscopic fibers, turning into pulp. Yes, that's the term. A gray, wet, slurry-like mass. At this stage, old boxes, newspapers, and letters lose their form and start a new cycle of life. The next step is cleaning the pulp to remove contaminants like plastic, glue, staples, and ink. It starts with screens of varying sizes. The pulp is pushed through under pressure, leaving larger debris like tape, staples, plastic bits, or thread behind. Smaller particles continue downstream. Then come the centrifuges. Remember physics class? In a centrifuge, everything spins, and heavier particles like sand or metal sink to the bottom, while lighter materials like plastic films rise to the top for separate removal. Water and centrifugal force work together, a perfect team. For ink removal, a process called de-inking is used. Foam made from soap and chemicals is added to the pulp. As the mixture spins, bubbles lift the ink to the surface, creating a frothy layer that carries the ink away. This method, called flotation, works like separating oil from water. Only here, it's ink instead of oil. Finally, the pulp is rinsed with clean water to remove any leftover chemicals or impurities, leaving a clean, fibrous mass ready for the next step, forming new paper. Let me know if you'd like further refinement or adjustments to the style. Glue, especially from labels or packaging, can be a real nuisance. During the cleaning process, it forms sticky clumps. To deal with this, special machines called tack removers capture those clumps before they ruin the final material. At this stage, the pulp is clean, light gray, or almost white, ready for the next step, forming new paper or cardboard. Old newspapers and boxes transform into material that can become packaging, napkins, or even part of furniture. Here's something fascinating. Paper can go through this recycling cycle 5 to 7 times before the fibers become too short for further processing. But until then, hooray, the paper's life continues. From the cleaned pulp, new sheets of paper or cardboard are created. The pulp is pressed, dried, and voila, a new product appears, the packaging for your favorite smoothie or a sleek notebook for your ideas. First, the pulp is spread into a thin, watery layer. It's poured onto a massive moving conveyor covered with a fine mesh, a sort of endless cloth that keeps moving. Water starts draining, and the pulp gradually thickens. This is where pressure takes the stage, turning the process into a true display of technical mastery. The first press, called the forming press, provides a gentle squeeze. Rollers press the pulp onto the moving mesh, evening out the thickness. These rollers are set at varying heights and pressures to make the pulp uniform. At this point, the pulp loses about half its water. Simply put, it goes from a watery mass to something resembling damp felt. Not yet paper, but with a clear structure. Next, the sheet moves to the second press, known as the smoothing press. Here, the pressure increases significantly. Heated rollers squeeze out the remaining water, speeding up the drying process. Not only does the paper or cardboard become thinner, but it also gains strength. At this stage, texture can be added. For instance, office paper gets a smooth finish, while packaging cardboard might have a more textured surface. This is achieved using rollers with patterned surfaces. After pressing, the sheet passes through a series of drying cylinders, massive metal drums heated from the inside. These cylinders reach temperatures of 260 degrees Fahrenheit, and the sheet glides over their surface. Moisture evaporates, leaving the paper or cardboard dry and strong. The cylinders press the sheet tightly against their hot surfaces, ensuring even and quick drying. Alongside the heat, hot air blowers are used to prevent uneven drying. After all, the paper needs to be consistently dry across its entire surface. During drying, the thickness of the final product can be controlled. For example, to make thin paper for notebooks or thick cardboard for boxes, adjustments are made to the roller pressure and the number of passes through the drying cylinders. Before the final drying stage, a special coating can be applied to the sheet, for instance, to give it a glossy finish. These coatings might include starch mixtures to strengthen the paper, or clay solutions for added shine. The coating is applied in a smooth layer using yet another roller. After drying, the sheet becomes a finished product. But it doesn't end there. It can be rolled into giant reels if it's destined for printing houses or factories. Alternatively, it can be cut into individual sheets like office paper. Here's a cool fact. One of the main goals of this entire process is to preserve the cellulose fiber's properties as much as possible. These fibers give paper its strength and flexibility. In a way, each sheet is the result of a symphony of machines and human ingenuity. Recycled paper becomes the foundation for thousands of new products. In the packaging industry, it's used for delivery boxes, shopping bags, and disposable cups. It can even turn into furniture or decor, creative cardboard chairs, lamps, or even bookshelves. These items are stylish and can last for years. Most commonly, paper is recycled into stationery, notebooks, folders, and even paper pens. Recycled paper is also ideal for creative projects like greeting cards, scrapbooks, or home decorations. It's amazing to think how an ordinary newspaper or box can live a brand new life. Instead of ending up in a landfill, it gets a second chance to become something useful. The production volume of French fries reaches 4 or even 5,000 tons per day. In the massive factories of the United States, the process of making French fries resembles a coordinated symphony of machinery, engineering expertise, and quality control. Production at facilities like McCain, Lamb Weston, or Simplot involves large-scale operations that make it possible to deliver tons of crispy fries to fast food restaurants, supermarkets, and food service establishments worldwide. Let's take a closer look at how this process works. Here we go. To make a delicious product, you need the best raw materials. Special varieties of potatoes, such as Russet Burbank or Innovator, are used for French fries. These varieties have a high starch content, ensuring the right texture and flavor. Factories receive millions of tons of potatoes from farming operations. A single large factory can process up to 1 million tons of potatoes annually. The potatoes are delivered by trucks that maintain optimal temperatures to prevent spoilage. Each truck typically carries between 20 and 30 tons of raw potatoes. To preserve quality, transportation happens immediately after harvest. At the factory, the truck backs onto a specialized platform that tilts the truck bed, allowing the potatoes to slide into a receiving hopper via gravity. Unloading a single truck takes less than 5 minutes. During peak season, a factory can handle up to 500 trucks per day. As the potatoes are unloaded, they undergo an initial inspection. Magnetic and mechanical separators are used to remove any metal or stone debris that might have been mixed in with the potatoes during harvesting. In the first stage, I observed how potatoes are washed in large automated drums using high-pressure water. A conveyor system evenly distributes the potatoes onto washing and sorting lines. Factories typically have their own wells or are connected to local water supply systems. Before use, the water undergoes multiple purification steps, including mechanical filtration, to eliminate impurities. Most factories recycle up to 90% of their water, significantly reducing costs. Water is delivered to the conveyor washing systems via powerful pumps that generate the necessary pressure for effective cleaning. Spray nozzles evenly distribute water over the potatoes as they move along the conveyor. The potatoes pass through rotating drums, where high-pressure water removes most of the dirt. Some factories use water baths with air bubbles for a gentler cleaning process, ensuring that dirt residues are removed without damaging the potatoes. This process thoroughly cleans the potatoes, removing soil, dirt, stones, and debris. The water used for washing is collected in reservoirs, where it is filtered to remove solid particles. Once purified, the water is recirculated back into the system. This setup saves thousands of gallons every day. To peel potatoes, special mechanical devices are used to leave only the clean, soft flesh. First, the potatoes pass through abrasive drums with walls coated in rough materials. As the drum rotates, the skin is scraped off, and the clean potatoes move along the line. This method is highly effective for large volumes, processing up to 20 tons of potatoes per hour. Next, the potatoes are placed in high-pressure chambers, where steam is introduced at a temperature of about 131 degrees Fahrenheit. Under pressure, the steam penetrates the skin, softening it. Afterward, the temperature difference and a strong airflow separate the skin from the potato. Following this initial cleaning, the potatoes are processed on polishing rollers to achieve a perfectly smooth surface. This step removes any tiny bits of skin or other imperfections. Why? Why didn't I have one of these chambers as a kid? I used to hate peeling potatoes. It could have been so simple, just whoosh, and the skin would be gone. Life is unfair. Next, the potatoes pass through high-speed cutting machines that slice them into the desired size and shape. There are plenty of options: classic fries, thick, home-style cuts, crinkle cuts, or even spiral. Personally, my favorite is the classic fry. What about you? These machines can cut more than 14 pounds of potatoes per hour. Did you know that several countries claim the origins of French fries? However, it was America that truly popularized them, spreading their deliciousness worldwide. The next process is called blanching. This step is critically important for achieving the perfect color, texture, and flavor. Sliced potatoes are immersed in hot water, approximately 86 degrees Fahrenheit, for 1 to 2 minutes. This process removes excess starch, enhances the color, and helps prevent the formation of harmful compounds during frying. After blanching, the potatoes are passed through drying systems that remove excess moisture. As I have been informed, this ensures a uniform texture and crispy crust. First, the potatoes are loaded onto a conveyor. Excess water initially drains naturally through openings in the conveyor. The potatoes are then transported into a drying chamber, where they are exposed to a powerful stream of hot air. The air temperature must not exceed 60 degrees Fahrenheit to avoid damaging the structure of the potatoes. Depending on the size of the slices, for standard thickness French fries, drying takes no more than 30 seconds. At this factory, the dryer can process up to 22,000 pounds of potatoes per hour. Potatoes are fried in vegetable oil, which can be corn oil, canola oil, or sunflower oil. The fryer temperature reaches 176 degrees Fahrenheit. The potatoes are fed into the fryer via a conveyor belt. On a side note, I'll let you in on a secret. My girlfriend seems to take baths at the same hellishly hot temperature as these poor potatoes, worn out by all the processing. Before frying, automated systems inspect the product once more to remove any overly small pieces that might burn. The calibrated potato pieces destined for frying are evenly distributed on the conveyor belt to prevent them from sticking together during the frying process. The potatoes move through the oil on the conveyor, submerging evenly to ensure consistent frying. During frying, the oil is continuously filtered to remove small potato particles and prevent overheating or oxidation. To avoid burns or the formation of bubbles on the surface of the product, the potatoes are gradually lifted out of the hot oil, ensuring a smooth temperature transition. The total immersion time is approximately 1 minute, just enough to create a light, crispy outer layer. After frying, the potatoes pass through tunnels with streams of cold air, which helps preserve the product's freshness and quality. Cooling French fries after frying is a crucial step in the production process, as it prepares the product for subsequent stages, such as freezing or packaging. The entire process is carried out quickly and meticulously. Cooling helps maintain the fries' crispiness and minimizes internal softening. Additionally, it prevents the formation of excess condensation, which could compromise quality during freezing. After frying, the potatoes are loaded onto specialized conveyors equipped with air tunnels. Powerful fans circulate cooled air through these tunnels, and their speed is adjustable to avoid damaging the fries. For uniform cooling, the potato pieces are continuously stirred or flipped on the conveyor belt. A single cooling tunnel can process up to 11,000 pounds of potatoes per hour. The potatoes are weighed and automatically packaged into bags of various sizes. One production line can package up to 150 bags per minute. Impressive speed, isn't it? The cooled or frozen fries are transferred onto specialized conveyor belts. Vibrating feeders evenly distribute the pieces along the belt, ensuring precise weighing. The scales analyze the fries in real time and select the optimal combination to achieve the target weight. After weighing, the potatoes move to packaging machines, where the bags are formed. There are generally two types of packaging: soft polyethylene bags for retail sales, and large paper or plastic sacks for restaurants. The machines seal the bags using heat-sealed seams, ensuring airtight packaging that protects the product from oxidation. Some bags are filled with nitrogen to preserve the fries' quality for longer periods. Once sealed, labels are applied to the packages, displaying product information such as weight, ingredients, production date, and expiration date. The finished product is stored in refrigerated warehouses, where a constant temperature of -8 degrees Fahrenheit is maintained. A single package of McDonald's French fries can pass through the entire factory process in under 60 minutes. Annually, more than 11 million tons of French fries are produced worldwide, with the majority manufactured in the United States. This entire process is a marvel of engineering, enabling billions of people to enjoy delicious and high-quality French fries. Ready to explode with curiosity? In this video, we're about to open some top-secret doors to the world of fireworks and firecrackers, things you never even knew existed. Stick around, and you'll see how a simple blend of gunpowder turns into the magic behind the brightest blasts. You'll get the lowdown on the wild history behind their creation and the unusual secrets of master pyrotechnicians. This segment will get your heart pounding faster, trust me. Watch till the end, because the best part is still ahead. Stay with us all the way through, and you'll find out something that'll totally flip your perspective. Don't miss out. Firecrackers, they're the more hot-headed guys in this family. Their main trick? It's all about the sound, not the show. Sure, they're simpler in design, but they deliver the same kind of magic. Noise and pure adrenaline. Like fireworks, firecrackers use black powder as their base, but the approach here is a bit more straightforward. The key is nailing the right balance to get a powerful boom without any extra fancy effects. Typically, a firecracker contains a black powder mixture, a casing, and a fuse. We'll get into what's inside later, but for now, let's talk about the casing. It's usually a paper or cardboard cylinder that holds everything together. The material's gotta be strong enough to hold off the blast till the big moment, but not so tough that it creates dangerous shrapnel. The fuse is the most critical part. It sets off the entire explosive process. It could be a thin cotton wick soaked in chemicals or more modern ignition systems. How are firecrackers made? All the ingredients for the black powder mix are measured out with serious precision, then blended to get the perfect consistency. Accuracy is huge here. Just a little extra saltpeter can make the explosion go wild. Too little, and the firecracker won't ignite at all. Paper or cardboard tubes are cut to the needed length, then carefully loaded with the black powder mixture. These casings typically have sealed ends to build up just the right pressure for the explosion. At the top of the firecracker, a small hole is made for the fuse. The fuse is inserted and held in place with glue or a special sealant. The bottom and top edges of the firecracker are sealed tightly, often using glue or heat bonding. This ensures safe storage and transportation. Next, the firecrackers undergo careful testing. Manufacturers check the sound level, ignition speed, and quality of the explosion. Not all firecrackers are created equal. Cheap ones often have uneven filling, weaker sound, and a bigger risk of misfiring. They use lower quality materials, like plain paper instead of sturdier cardboard. High-quality firecracker casings are made from sturdy yet lightweight material. The black powder mixture inside is evenly distributed for a consistent effect. The fuses have a precise burn time to give you enough seconds to back off to a safe distance. Making firecrackers is no joke. Pyrotechnics plants follow strict safety rules. Workers operate in small crews, wear anti-static clothing, and handle only minimal amounts of mixture at any one time to reduce the risk of accidental explosions. Why are firecrackers so loud? This question comes up a lot. The deal is, a firecracker's explosion isn't just a chemical reaction. It's a massive release of energy in a confined space. When the powder burns, it releases hot gases that expand super fast, creating a powerful shockwave. And since the casing is tightly packed, that wave comes with the trademark boom sound we all know. The word firecracker comes from the French pétard, meaning a blast. Like fireworks, firecrackers trace their roots back to China. Initially, they were used to scare off evil spirits, and only later did they become a popular form of entertainment. Today, firecrackers are an essential part of many celebrations and festivals around the globe. But their history shows that even the simplest things can have deep roots and a fascinating evolution. So, the next time you hear that familiar bang, remember just how much skill, history, and technique is packed into each tiny firecracker. When it comes to making fireworks, you also start by mixing gunpowder with other components. If you think of gunpowder as the engine of the firework, then the other materials are the artists who create that explosion of color, light, and shape. To get bright sparks, you need metal powders like aluminum, magnesium, and titanium shavings. For vivid colors, you rely on metal salts such as strontium, barium, copper, and sodium. To boost the energy of the blast, you add ingredients like potassium nitrate, perchlorates, and charcoal. These act as oxidizers and fuels. And to hold it all together, you use binding agents, like water-soluble glues. Each component is first ground into the finest possible powder. Picture shining metal particles dancing in the light as the master prepares them for blending. These powders are so lightweight, it's almost as if they're suspended in midair, like some kind of magical dust. The most important step starts when the ingredients go into a mill filled with ceramic or wooden balls. These balls rotate gently, grinding the mix into a perfectly uniform blend. There's a soft rustle and a light tapping sound, kind of a subtle rhythm, reminding you that a future burst of colors is being born. As for mixing the ingredients by hand, at traditional production sites, this step is done with great care and reverence. Specialists slowly and carefully blend the ingredients with wooden or copper paddles. Why so slow? Because even a single stray spark could set the whole thing off. The mixture looks like a shimmering sand, where each component has its role to play. To avoid accidental explosions, the mixture is often moistened. Water doesn't just make the process safer, it adds a sort of mysterious alchemy, as gunpowder and colorants form tiny granules. The smallest mistake can cause a tragedy. You know what pyrotechnic masters do before they start working? They remove all metal objects, even wedding rings, to prevent sparks. In many labs, cell phones are strictly forbidden, and employees wear anti-static clothing. Even the air matters. Conditions are kept humid enough so that mixes don't dry out and become dangerously volatile. Before packing the mixture into the casing, the masters test how it burns. A small sample is ignited, and everyone holds their breath. Is that the perfect shade of blue? Are the sparks bright enough? It's like a dress rehearsal before the big show. Creating shapes and colors. That's the coolest part of production. Want a heart or a star in the sky? It all depends on how the stars are arranged. These are tiny pellets with a special composition. Where'd those brilliant reds, greens, and blues come from? All thanks to chemical compounds. For instance, barium makes green, strontium makes red, and copper makes blue. Once all the components are prepped, the next crucial step is filling the casing, where the heart of the future firework is born. It's right here that the explosive mix and colorants become a finished product, capable of painting the night sky in every color of the rainbow. The casing is a shell that holds all the fireworks parts together. It's made from special materials that can handle high pressure and heat, yet remain light enough to shoot into the sky. Cylindrical shapes are perfect for forming sharp patterns like rings, chrysanthemums, or peonies, while spherical shells create symmetrical three-dimensional effects, like a glowing orb exploding into hundreds of sparks. The filling process is super important, because the exact placement of components ensures the desired effect. Let's break it down step by step. First, you take cylindrical or spherical shells, usually made of cardboard, plastic, or specially treated paper with fire-resistant properties. Spheres typically come in two halves that will be joined later. It's crucial that the casing is airtight. That guarantees the explosion happens at the right moment with the right intensity. The black powder charge, acting as the main engine, sits at the center. It's responsible for propelling the firework skyward and making sure it explodes properly. Around that charge, the colorants and special effect mixtures are arranged. Each tiny star element is placed by hand or using special machines. These stars are what we call the pellets that burn in the sky. For spherical shells, these stars are placed evenly, so that when it explodes, it forms a perfect sphere of light. In cylindrical shells, charges are often laid in layers or formed into specific patterns, depending on the planned effect. One standard spherical firework can hold about 200 to 300 pellets. Large, multi-layer shells might have over 1,000 of them. To ensure the firework explodes at the right time, a time delay fuse is added. A small tube filled with a slower burning composition. This timer connects to the main charge, providing a delay between the rocket's launch and the burst in the sky. After all elements are in place, they're secured with a special paste or paper spacers. This keeps every component locked in position during the launch. The casing might then be wound tightly with string or glued for extra rigidity. Crafting one large professional-grade firework can take up to 4 hours, considering all the careful assembly and testing. For a massive show with several thousand shells, pyrotechnicians might work for a few months straight. The spherical shape is the classic standard in pyrotechnics, giving an even spread of stars and creating that perfect circular effect. Filling such a shell requires even more skill. Each star is placed by hand around the central charge. It's all on the master's shoulders. How the components are arranged will define how the explosion looks. For example, to create a smiley face in the sky, the pellets are laid out in the shape of a face. When the powder ignites, those pellets spread out just right, forming the intended pattern. Every year, over 200,000 short tons of fireworks are produced worldwide. China is the leader here, accounting for about 90% of the global output. For major holidays, like Independence Day in the United States or New Year's Eve in Sydney, up to 10,000 separate fireworks might be launched in a single night. Such a display can last over 20 minutes and sometimes costs as much as $5 million. Despite the beauty of fireworks, safety stats are pretty alarming. In the United States each year, up to 10,000 injuries are reported due to improper use of pyrotechnics, with about 70% of the injured being young people under 20 years old.